We are now going to talk about and develop our quantitative, not qualitative, understanding of microphase separation. So let's start in our disordered state. So when our thing is just mixed. And so we could use a lot of our expressions and approximate it from Flory-Huggins theory. So we know that from Flory-Huggins theory for mixing, we're going to have delta G of mixing equals delta H of mixing minus T delta S of mixing. So I will say in general that it's very reasonable to kind of keep this delta H of mixing the same as we've seen previously. And you can kind of see it right here. So all we're doing is we're using that same mixing term. That is a very, very good, easy or not a justifiable approximation to make. So in the disordered state, again, your A and B chains are touching. So it's just going to be these number of AB interactions, volume fraction, the usual suspects that we've been dealing with. But where's my delta S of mixing contribution here? Why didn't I write out delta G here? Why is it just the enthalpy in that disordered state? If I'm looking at the total free energy contributions in this disordered state, D. Well, delta S of mixing is going to be very small, like we talked about in the last video. Why? Because our delta S of mixing is scaled by these 1 over x1 plus these 1 over x2 terms. And we know that x1, x2, or equivalently NA and NB, are going to be very, very, very large. So in terms of magnitude here, this is going to be very, very, very small, and you could almost, essentially, you can neglect it. So, and then we saw this last time in the exam and in previous discussions where when you're mixing, two polymers, those delta S mixing terms, the magnitude is going to be very, very, very small. So, also, it's a little bit kind of difficult to look. The delta S mixing is reduced even further because they're not truly separate components. So they're chemically linked. So previously we had like a homopolymer here, a homopolymer here. When they were mixing, instead of in the phase separated state, we had some translational entropy here, translational entropy of here, and we could reconfigure the number of microstates. But when they're chemically linked, those translational entropy, those distinct number of microstates are even reduced even further. So really that delta S mixing term is going to be negative. So we're going to cut it out, cancel it. So it's not going to really play a role at all here in this. So really for the disordered state, in terms of energy, is just going to be this enthalpic driving force actually to move towards the ordered state because those AB interactions are unfavorable. So ordered state, again, why don't we have one of the other in the ordered state here? So these are just AB touching. Again, those are the interactions. We don't need to consider our AA or our BB interactions. Why? Because they're just 0. Now in the ordered state, right here, so ordered, here, we are going to have, again, there's going to be a lot of AA interactions on this side. There's going to be a lot of BB interactions, but again, they don't matter because right here. So really, we only care about this IMDS, intermaterial dividing surface, those AB contacts here. And so the interfacial energy here is just going to be given by the interfacial area, or interfacial energy per area times the interfacial area. That's going to give me my interfacial energy here, those number of AB contacts. So that is going to be my delta H, my delta H in that ordered state. So now, actually, forget about the delta. Excuse me. That's a typo there. So that's the enthalpy in the ordered state. Now, what else is happening here? So again, there's those AB interactions, AA, BB, don't matter. What else is happening here? Well, we talked about last time, there's that delta H of stretching. So because we want to avoid those AB contacts, we need to account for that conformational entropy of our polymer chains. So those need to stretch out in order to minimize, again, that min-max principle, minimize interfacial energy, maximize conformations, and instead, minimize instead of maximizing those same, we want to maximize these favorable interactions. So when they stretch out, you can think of it one way or the other. So we can minimize the number of AB contacts, or we can maximize the number of AA contacts here. We have that expression for delta S of stretching. We've done that in many previous lectures, 3 and 4, and you've seen it pop up many, many times before. And it's just this term right here. So this is our delta S of stretching, and specifically the change from the ordered to the disordered state, we have to just basically subtract by 1 because that is going to be in our unstretched state. So you could have this expression here because in the unstretched state, it's just going to be the same value. So you could see if our ordered was completely unstretched, so if R squared was equal to R naught squared, which is equal to basically NL squared in our old format, or NA squared in our new format, or kind of this lambda over 2 squared. So actually, if that was this, then our delta S of stretching, you can see here, would be equal to 0. So there would be no change in stretching because this value would just be 1. So if this is the case, we don't have to deal with it. But we know that this R, we are going to be stretched. And actually, we can look back at our value here. We're going to be stretched some length lambda over 2. So this is going to be, again, the length that we're dealing with, the amount that we're stretched. So go back here. So we can substitute, again, undeformed length. So just in our ideal state, that R naught squared is going to be equal to NA squared. But our R squared, in that fully stretched out state like this, the length of our polymer is going to be this lambda over 2. So our R squared is going to be lambda over 2 squared. So we can replace this, and then you just kind of rewrite now the full free energy change, or the total free energy change from our, again, delta G from our order-disorder transition, you could call it that. Remember, we only had one delta H. We had enthalpy of our ordered state minus, because again, we're going from delta G from our ordered to disordered state. So ordered state, this was the term right here, just our interfacial energy. Disordered state, that comes from our Flory-Huggins theory. Again, in that mixed state, essentially, here. So this is the contribution when we're mixed in the disordered. And this is just your delta S, your stretching term, right here. So you have these two enthalpic contributions. We'll see that in a second. Enthalpic, and one entropic driving force. We're going to see where they push, or where they want our system to go in just a second. Now, we can now make this assumption, this incompressibility assumption. So there's a volume conservation condition. So this is true once we're basically both of these are equivalent. These the volume of the segment times the number of segment. Second term is just the size of the domain times the interfacial area. These are equal when the chain is stretched to the final state. So once we reach this amount of stretching, this lambda over 2, we can set that these volumes equal to one another. So we can use this expression, plug back in, and rewrite, and really kind of just get rid of this nasty this nasty sigma over here. So we can rewrite this as lambda over, as just substitute it in and get rid of this guy. So we're going to substitute in because we have this expression, which again you could look it up in Frederickson's book and derive it yourself, or you could trust me, and then we're just plugging in over here for sigma. So now everything's in kind of nice terms that we want to deal with. So now, what is the goal of this kind of lecture, aside from doing a really nice derivation? Well, we want to figure out, okay, how stretched out are these chains? What is kind of the period, the optimum period of my lamella repeat unit? Because again, that's going to change. The whole focus of this microphase separation discussion is we want to be able to control microstructures. So I might have an application where I want, if I'm designing a circuit like with graphoepitaxy, like we talked about previously, I might want to change the size or the spacing of this lamellar blocks, this lambda over 2 for my circuit. But I'm going to need to kind of figure out, okay, how, depending on all these different parameters, specifically my Chi-A-B for my materials and volume fractions and number of polymer units and N, how is my period going to change? And also, the other critical question is, when will I phase separate? When will I microphase separate? Those are two critical questions that we want to answer with this derivation. So let's keep going for a little bit further. But first, before we get into finding that period, which is going to be a little bit mathematical, let's take a big step back. So this is my full free energy contribution. One of the key assumptions we made here was that for our disordered state, that delta S of mixing is essentially 0. So what in here is pushing us to go to a disordered state? Well, it's the stretching term. We want to maximize our conformational entropy, so I want to be in the disordered state. So that's what's pushing us to go to disordered. What's pushing us to go to our ordered state? Well, it's this minimization of these enthalpic interactions. So enthalpy pushes us to go to our ordered state, minimizing those AB interactions, but the delta S of our conformational entropy loss will push us, in order to maximize our conformational entropy, we want to be in that disordered state. So that's the big high-level picture that you want to have in this derivation. Now, if I want to figure out how does my period, or what's the size of that optimum period, well, I need to just take basically if I want to figure out what is the optimum period, what is my kind of the maximum, or what's the optimal value here, I'm just going to take the derivative of our expression here with respect to lambda, except not obviously with the sigma. I'm going to use this nice expression that we developed previously. And the problem is that you'll actually calculate this out explicitly. So I'm going to use this expression. I'm going to take the derivative with respect to lambda and see at what lambda is my free energy minimized. That's going to be my optimum lambda. And you can see here, there's some really interesting scaling behavior here. So lambda scales with n to the 2/3. What does this tell you? What does this scaling tell you about how stretched out these chains are? The chains are really, really extended because this is basically 66, 0.66. For a really, really, really good solvent, we're just at 0.6. So, and we're really large compared to our melt state. So these chains are very, very extended in order to minimize those AB interactions. So what does this mean? And actually, you could also see, again, this kind of makes sense too. As my chi-AB increases, my optimal period increases as well, right? So as my chi-AB, those AB interactions become less favorable, my optimum period, they become even more stretched, right? So, because they want to minimize those AB interactions. There'll be another problem set question on that one as well. Now, this is great, but again, what is my critical chi parameter? What is my critical chi NAB that will allow me to phase separate, microphase separate, or not microphase separate? Well, we can see that we've basically said this dependence on molecular weight if we're in the phase separated state, but we haven't determined when that occurs. Well, the way that we can find the critical chi-AB for this order-disorder transition, we have basically this optimal lambda for when we are phase separated. So let's plug in this lambda optimal and figure out when does delta G equal 0. Because when we're in equilibrium, that means that where order-disorder is equally probable once we have this optimal lambda. So plug in, figure out when, this should be, again, substitute for the optimal lambda, which will yield most negative possible value for free energy. If this is less than 0, ordering should occur. So again, similar idea. We're just plugging in. Once you have that lambda optimal, that delta G should be equal to 0. That's going to be my most negative value when we're at equilibrium. So let's see when ordering will occur. So you can do some simplifications. You'll be asked to do this in the problem set. But eventually, at the end of the day, what you'll get is you have this critical chi parameter, microphase separation. So microphase separation. Your critical chi ABN is equal to 10.5. This is unbelievable to me. Why? What was our critical chi n parameter for basically for macrophase separation for two polymers? Well, go back into lecture 4, chi ABN, you do some flipping. It was 2. Look at how much higher we have to be in chi ABN in order to microphase separate. So look at how much greater that is. Almost, we're almost half an order of magnitude. It's so much more difficult to microphase separate than to macrophase separate. So why was that? So in macrophase separation, we had our, basically our ordered system where we're, basically phase separated. Then we had, so this is our ordered effectively, and we had our mixed state. So unmixed and then mixed state. So multiple polymers mixing. So what was the driving force for mixing here? It was just that delta S of mix, right? And here was our same delta H. But for our microphase separated state, what's our driving force energetically to mix, to become disordered? This stretching term. So it shows you the power of these changes in conformational entropy of the polymer chains, that they really, really don't want to be extended to n to the 2/3. That is really unfavorable in terms of our delta S conformation. So it's going to take a lot larger, basically enthalpic driving force or unfavorable AB interactions in order to push it into that microphase separated state. So this, and thus, we need to, again, macrophase separation, Chain's ideal did not stretch, but now we're stretching, so we need to decrease temperature way more, or again, basically increase like those unfavorable interactions way more to basically avoid this additional entropy term here. So which is much greater than the entropy of mixing. So that raises that chi-n. So this matches again with that qualitative analysis. And there's lots of kind of cool phase diagram behavior that we're going to talk about in the next video. So this is the power of stretching, and it's the power of this loss of conformational entropy. So I really, really like this derivation. You'll be getting several problems on the problem set about this, but again, don't get lost too much in the math, conceptual ideas. Look at that lambda optimal, look at that chi-n-AB, and be able to explain, that power of stretching is unbelievable when you look at the kind of the math and the implications that this has for your system. So next time we're going to be looking at, we only did this for 50-50, but as you can see in our presentation right here, there are lots of different phases that are possible. We are not going to go through those derivations because it is fairly difficult to do so, but we will next time look at some of these graphs in a second. Actually, we're going to look at our presentation or our lecture notes instead. So I'll see you all in the next video. Thanks. Bye.